So let's talk about various number systems. Specifically, we'll talk about binary number systems. So let's start by talking about a number system that we've all been using for many years, the decimal number system. Decimal refers to base 10 number systems, not just those with a decimal point. So we have decimal numbers, base 10. Here's an example, 5,374. This is the ones place, or we could write it also as the 10 to the zeros place, right? 10 is the base. This is the 10 to the ones place, or the tens place. This is the hundreds place, or the 10 to the twos place. And here's our thousands place, or the 10 to the threes place. And so we find the value by multiplying the value in each weight or each place, and then adding them together. So for example, we have 4 times the weight, the 10 to the zeros place, or the ones place, plus 7 times that weight, or the 10 to the ones place, the tens place, plus 3 times the 10 to the twos, or a hundreds place, plus 5 times that place, or that weight, the 10 to the threes, or thousands place. We add those all together to get the value. It's just the principles are the same in binary numbers. So here we have instead of 10 to the zeros place, right, we have base 10 to the zeros place, 10 to the 1, 10 to the 2, 10 to the threes place. Now we're going to have base 2 to the zeros place, still 1, right, still our ones column, or ones place. Now we have the 2 to the ones place, or the twos column. Now the 2 to the twos place, or the fours column. And finally the 2 to the threes place, or the eights column. And we could go on, right? We could have a larger number, 2 to the fours place, or the 16s place, 2 to the 5 or 32s place, 2 to the 6 or 64s place, and so on. And so to find out what value this represents, we multiply the value in that weight or that place by the weight and add them all together. So here we have a 1 times 2 to the 0, or ones place, plus, 0 times 2 to the 1, or the twos place, plus 1 times the 2 to the twos place, or the fours place, and finally plus 1 times 2 to the threes place, or the eights place. And so we have all of these values, and we can get we have 1 times 8, we have 8, plus 1 times 4, 4, plus, we don't have anything in the twos place, but we do in the ones place. And so we get 8 plus 4 plus 1, 12 plus 1, 8 plus 4 is 12, plus 1 equals 13 base 10. And so 1101 in binary is 13 base 10. And one thing you'll notice here is that one nice thing about binary is we don't really have to do 1 times. We can say, well, it's either there or not, right? Well, we have a 2 to the threes place that has a 1 in it, 2 to the 2 has a 1 in it, and 2 to the 0 has a 1 in it. So we add those 3. We have 8 plus 4 plus 1. 8 plus 4 plus 1. So we can also count in binary just like we can in decimal. So in decimal we'd have 0, 1, 2, blah, 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 3, 4, 5, 6, 7, 8, 9. When we got to 9, we'd have to go to the next digit. We get 10, blah, 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 blah. And so in binary, here we have 0, 1. And now at 2, we can it no longer fits in a single digit. So we go to a second digit here, and we get 1, 0. So we have a 1 in the twos place, that's equal to 2. And now we have a 1 in the twos place and a 1 in the ones place to get 2 plus 1 or 3. And now we can no longer use 2 digits. We filled them up with our 1s. And so now we go to a third bit. We get a 1 in the 4th place to get 4. 1 in the 4th place plus a 1 in the 1s place to get 5. And so forth, right? We have 6, 7, 8, and so on. And so it's really handy to memorize powers of 2 because we're going to use them a lot. So here, for example, we have the 2 to the 0th place, or 2 to the 0th power is 1, 2 to the 1, 2 to the 2, 4, 2 to the 3, 8, 2 to the 4, 16, 2 to the 5, 32, 2 to the 6, 64, 2 to the 7, 128, 2 to the 8, 256, 2 to the 9, 512, 2 to the 10, 1024, 2 to the 11, 2048, 4096, 81, 92, and so forth. And so these powers of 2 are really handy to memorize, at least up to 2 to the 10. And then you can memorize the other ones as well. But definitely memorize at least these because we're going to use them a lot. And so if you make errors in the powers of 2, they'll propagate to errors in your other calculations. So let's talk about number conversion specifically. So we actually did this already. We converted from binary to decimal. Let's do it again. So we want to convert this binary number, and you can tell the base by that subscript 2, base 2. So we have this binary number 10011, convert it to decimal. So now would be a good time to pause the video, try that out on your own, and then we'll work it out together as well. So 10011 base 2 is, well, we have a 1 in the 1's place, a 1 in the 2's place. We don't have a 1 in the 4 or the 8's place, but we do in the 16's place. And so we get 16 plus 2 plus 1 is equal to 19 base 10. So this is our binary representation of 19. Now, decimal to binary conversion, we're going to find the largest power of 2 that fits in the decimal number, and then put a 1 there and subtract. So let's show how this is done. Here we have the 1, 2, 4, 8, 16, 32. Well, 32 is the largest power of 2 that'll fit in 47. 64 is too big. So we put a 1 in the 32's place. And if that's all we did, if we had zeros everywhere else, well, this would be the binary representation of 32. That's not quite what we want. Let's see, we got 47 minus 32, and so we get 15. Okay, and it's good to put the weights down here, 1, 2, 4, 8, 16, 32. And so here we have our, we want 15, we want to see, now we want to add 15 basically to that number. So 16 wouldn't fit, 16 is too big, so we put a 0 there, but 8 would. 8 fits into 15. So we put a 1 there and subtract 8, we get 7. Okay, does 4 fit into 7? Yes. Minus 4, we get 3. Does 2 fit into 3? Yep. And finally, we put our last 1 in the 1's place, and we get down to 0. So we have 32 plus 8 plus 4 plus 2 plus 1 is equal to 47. So here's our binary representation of the value 47. And we can double check it, right, by adding. Usually it's easier to start from the other side. 1 plus 2 plus 4 plus 8 plus 32. There's no 16, but there is a 32. So we have 32 plus 8, 40, plus 4, 44, 45, 46, 47. There are two methods for finding the binary representation of a decimal number. So method 1, which we showed a few slides ago, where we find the largest power of 2 that fits, subtract and repeat. And then there's a second method where we repeatedly divide by the base, in this case 2, and the remainder goes in the next significant bits. So let's show both of these methods. So here's method 1. We want to convert the decimal number 53 to base 2 or to binary.
So pause your video right now and try to convert this number 53 into a binary number using the method we showed a few slides ago, where we find the largest power of 2 that fits, subtract that number from 53, and continue until we get 0. Okay, so let's see what we do. So 53, let's find the largest power of 2 that fits. 1, 2, 4, 8, 16, 32 is the largest. 64 is too big. So 1, 2, 4, 8, 16, 32. So we put a 1 in the 32's place. If that was the only one we had, all the rest of the weights were 0, then this value would be the binary representation of 32. So that's not what we want, but let's see what we do from there. So minus 32, we get 21. Okay, well, does 16 fit? Yeah, 16 fits into 21, so we put a 1 in that place. We get 5. Okay, 8 doesn't fit, so there's a 0 there, but 4 does. So we put a 1 in the 4's place. Subtract that from 5. We get 1. And finally, does 2 fit? No, but 1 does. And so we put a 1 in the 1's place. We get 1 minus 1 equals 0. And we get our binary representation of 53. And, we can double check that by adding up the weights, right? 1 plus 4 plus 16 plus 32. Basically, kind of going back and redoing what we, kind of going the reverse direction from what we just did. Okay, so now let's show the second method, which is repeatedly divide by 2. So let's start with decimal numbers because we're all used to those. So let's suppose we have some other number making this up, 486 or something, and this is base 10. So if we divide by the base, whatever it is, in this case we're going to divide by base 10, and then we would get 48 remainder 6. And this 6, this remainder, goes into the least significant digit. And then we keep going. We take the quotient here, and we get 48 divided by 10 is 4 remainder 8. This remainder goes to the next most significant digit. And then finally we take this last quotient, 4 divided by 10, and we get 0 remainder 4. That remainder goes into our next most significant digit. And we got down to 0, so we're done. And, we're going to decimal, so this is pretty straightforward, but the same method works for no matter what base it is. So now we're just going to change the base to base 2, or we could change it to other bases, whatever base we're converting to. Okay, so now let's take our number and do that same method for base 2. So 53, base 10. We're going to divide it by the base, in this case base 2. We want to convert to binary. And so we're going to get 26 remainder 1. And so remember that remainder is what goes in the least significant bit. And then we continue and say, okay, well, take our quotient 26. 26 divided by 2 is 13. Remainder 0. That goes in the next most significant bit. And now we're going to take that quotient 13 divided by 2. We're going to get 6 remainder 1. That remainder goes in our next most significant bit. And now we have 6, our quotient 6 divided by 2. We're going to get 3 remainder 0. That goes in our next most significant bit. And now we're going to get 3 divided by 2 is equal to 1, remainder 1. That remainder goes into our next most significant bit. And finally, we're going to get 1 divided by 2, and we get 0, remainder 1. And so that's our last bit. We got down to 0, so we're done. And we see that, hey, in fact, this is exactly the same as what we got with method 1. And it should be, right? The methods are different, but the results should be the same. The binary representation of 53. And remember, this could be any base. We convert to other bases as well. So if we were converting 53 to base 5, for example, now instead of dividing by 2, right? So for binary, we're using base 2, would use base 5. Our base is 5, so we divide by 5, and we get 10, remainder 3. So 3 would go in our least significant digit. These are now base 5 digits. Take our 10 here, our quotient, 10 divided by 5 equals 2, remainder 0. 0 goes in our next most significant digit. And now we take our last quotient, 2 divided by 5, and we get 0, remainder 2. And we're done because we got down to 0. And so 53 in base 5 representation, remember this the subscript indicates the base. So 53 base 10 is equal to 203 base 5. And we can double check this. Well, let's see, this position here, this weight is the 5 to the 0 place, or the 1's place. This is 5 to the 1's place, the 5's place, and this is 5 to the 2's place, or 25. And so we're going to get 2 times 25 plus 3 times 1. And we get 50 plus 3 equals 53. So we just double check that. So this method 2, again, is recommended for other bases, but for converting from decimal to base 2 or to binary, method 1 is recommended because it's easier. We're dealing with, subtraction instead of division, less likely to have errors with that. But method 2 is used for other bases. Method 1 for binary. So binary values, just like decimal values, have a range and a number of values that you can represent. So let's first look at decimal numbers because we're used to those. So let's suppose we have a 3-digit decimal number. So what is the range of that number? Well, let's see, the smallest number with 3 digits we can represent is 0. And the largest number is 999. So that's the range of our 3-digit decimal number. We can also write that as 0 to 999. That's the range of our numbers. And the number of values we can represent, well, we can represent 1 to 99, so that's 999 values plus 0. So we can represent 1,000 different values. So this is the range, and we can represent 1,000 different values. And you may notice 1,000 is equal to 10 to the 3 values. And so if we had a 4-digit decimal number, we could represent 10 to the 4 values and go from 0 to, well, you'll notice the range is 0 to, well, it's almost 10 to the 3, it's almost 1,000, but minus 1. 0 to 10 to the 3 minus 1 is another way for us to write that range. And so then we can see that, well, for a 4-bit or 4-digit decimal number, if we had a 4-digit decimal number, our range would be 0 to 10 to the 4 minus 1, or 10,000 minus 1. 5-digit, 0 to 10 to the 5 minus 1. And so now we see this pattern and see that, well, for any n, we can represent 10 to the n values, and the range is 0 to 10 to the n minus 1, where n is the number of digits. So in this case we have 3, but n can be any value. For n-bit binary numbers, well, we're going to see a similar pattern. So, well, what's the range? Let's start with that. The range is, well, what's the smallest number we can represent? The range, smallest number we can represent is 0, 0, 0, or just 0. And the largest number we can represent is 1, 1, 1. And that value is 1 plus 2 plus 4, or 7. So our range is from 0 to 7. And how many values can we represent? Well, we can represent the numbers 1 to 7, that's 7 values, plus 0. So that's 8 values. So the number of values we can represent is 8. 8 unique values. And we can, we could do another example. What could we represent with a 4-bit binary number? Well, the range would be 0, 0, 0, 0, or just 0 to 1, 1, 1, 1, which is 1 plus 2 plus 4 plus 8, which is 15. So our range would be 0 to 15. So we can write that in decimal too. 0 to 15. How many values would we have? So this is our range. And the number of values we can represent is, well, 1 to 15. So we have 15 values there, plus 0. And so we would have then 16 unique values. And so again, we'll see a pattern here, and we also can look at our base 10 numbers. Well, the number of values we can represent is 2 to the, well, in this case, 8 is 2 to the 3, and generically for any n, it's 2 to the n, where n is our n-bit, the number of bits that we're using. So we can represent 2 to the n values, and our range goes from 0 to almost 2 to the n, but 2 to the n minus 1. And so again, for n-bit binary numbers, we can represent 2 to the n, so the base to the nth power, where again, n is the number of bits we're using, and the range is 0 to 2 to the n minus 1. And here's our example with our 3-bit binary number. And so we can generalize this now for any bit binary number.